Good morning, students. Welcome back after the online test. Hope you have done well. Today, uh, our topic would be the behavior of dielectrics and conductors in presence of external electric field. We shall be basically paying more attention to dielectrics because if you remember last class we have discussed behavior of conductors under the influence of electric field. So we have discussed last class electrostatics of conductors. Now before we begin, the first thing that I would like to discuss is the behavior of a conductor and a dielectric in presence of external electric field E0. Suppose in a region there is some external electric field as represented by these red arrows. First, we have already discussed about conductors, what happens. The basic difference between conductor and dielectric is that conductors have large number of free electrons, whereas the electrons in case of dielectric are bound electrons. It's not that bound electrons are not present in conductors. Conductors have both bound as well as some free electrons. But all the electrons in case of dielectrics are bound. Bound means they are bound to the nucleus, they can't move here and there. Whereas the electrons, some of the electrons are free in a conductor, free in the sense they can move under application of some external field, they can move from one point to the other point. And that creates lot of differences between the properties of conductors and dielectric. So let's see what happens in case of conductor first. Imagine this electric field to be towards right as shown in the figure. If there be some free electrons, the bound electrons will also experience some force, but they are held tightly by the nucleus, so they will remain there. But the free electrons in the conductors, what would happen? They will experience a force. You know that force on a charged particle is given by the formula Q times E. Now these charges are free electrons which are negatively charged. Since it is negatively charged, it will experience a force in a direction opposite to the direction of electric field. Electric field E0 is towards right. So the force on these electrons will be towards left. So these free electrons will shift towards left. So the free electrons will move in this particular direction and they will accumulate over here. If the free electrons accumulate at the left end, and here there will be deficiency of electrons because this part will lose the electrons. So here there will be deficiency of electrons resulting in development of what kind of charge? Positive charge. And here the accumulation of electrons will result in what kind of charge? Negative charge. So this is the behavior in case of conductors. Now the moment there is transfer of electrons from one end to the other, you see this is positively charged end, this is negatively charged end. This would create an electric field within the conductor that would write as E in. This is E in. That means this is electric field due to these induced charges. And already there is external field E0. So understand the difference between these two fields. E0 is the field which is already present. It is the external field. E in was not present earlier. When we put the conductor in the region of electric field E0, then some of the electrons which are free to move from one end to the other, resulting in positive and negative charges at opposite ends as shown. And these induced charges, these free charges create an electric field which we write as E in. Initially E0 is more, E in is less, so there is net electric field towards right, electrons will move towards left. This process will then continue as long as more and more positive and negative charges develop on the opposite faces, resulting in increasing value of E in. So this value of electric field E in goes on increasing till it ultimately becomes equal to E0. And what would happen then? If these two fields become equal, in magnitude, they will cancel completely, and therefore the net electric field E net, which is the vector sum of E naught and E in. So it is E naught vector plus E in vector, that will be how much? 0. That is what you have to remember. Whatever be the value of external electric field, inside the conductor, the net electric field will be 0 because of the cancellation of the two fields E naught vector and E in vector. So E in vector is developed opposite to the direction of external field, and its magnitude quickly becomes equal to the value of E naught, and therefore they cancel completely, resulting in 0 electric field inside a conductor. This is what we have already discussed in case of electrostatics of conductors. Let's see what happens in case of dielectric. Before that, let me tell you, these positive charges are due to the free electrons movement from this end to this end. So this charge density that is developed, we call them as plus sigma free, and here we can call them as negative of sigma free. Free here simply indicates the movement of free electrons. That has resulted in formation of these surface charge densities. In case of dielectric, let's see what happens. So as in case of dielectrics, we don't have free electrons, we have only bound electrons, so it's not possible that electrons will move from one end to the other end. So this is the external field, which we have written as E naught vector. Now this dielectric is made up of molecules. We will see afterwards, it can be of two types, either polar molecules or non-polar molecules. The mechanism I will discuss afterwards, but due to some reason here also there will be development of positive charges at one end and negative charges at the other end. Why does this happen? Shortly I will discuss. But let me tell you one thing, that this development of positive and negative charges is not due to flow of electrons from this point, this end to the other end, as in case of conductors. It is due to some other reasons, two reasons. One is stretching, keywords you should remember. Other one is reorientation of dipoles. Now what is the meaning of this? I will explain to you in a short while. The difference, second difference is that between conductors and dielectrics, these positive and negative charges are due to bound charges. So we call them as sigma b. In some textbooks they also write as sigma p, and this they write as minus sigma p, where p stands for polarization. Whenever a dielectric is placed in external electric field, remember, charges are developed on its opposite faces normal to the direction of electric field. This phenomenon is called as polarization. So polarisation, and hence these surface charge densities we have denoted as minus sigma p and plus sigma p. Let me repeat the definition for polarization. Whenever a dielectric is placed in external electric field, then opposite charges, positive and negative, are induced on the opposite faces of the dielectric normal to the direction of electric field. This phenomenon is called as polarization. The surface charge densities we denote by plus sigma p and minus sigma p. So this is positive, this is negative, so there will be some electric field in opposite direction, like so. So this will be our E in vector. But the difference between these two is that this E in vector will be smaller in magnitude compared to the external electric field. Here the free electrons continue to move in case of conductors till both these vectors become equal in magnitude. But in case of dielectrics, this field E in vector is smaller in magnitude compared to E naught vector, and therefore although they are in opposite direction, complete cancellation does not take place. Therefore E net vector in this case will not be equal to 0. So E net is not equal to 0. Here the net electric field is equal to 0. So that is one prime important difference between conductors and dielectrics. Remember, in case of conductors, inside the conductor the net electric field will always be 0. In case of insulators or dielectrics, inside the dielectric the net electric field is not equal to 0. Then what will be the direction of net electric field? So E net will be in this particular direction. You can see this is greater. It is in the direction of external field. Now I told you that in short while I will explain how come these positive and negative charges develop due to polarization in case of dielectrics. So that would be our next topic. Let's see one by one. Okay. Before discussing the mechanism of polarization by stretching and reorientation in case of dielectrics, it's important to know what is the difference between polar and non-polar molecules. A polar molecule is, for example, hydrogen chloride, HCl. Now in this particular molecule, one electron of hydrogen and other electron of chlorine, they share each other to form a shared pair of electrons. This kind of bond, it is called as covalent bond. But this shared pair of electron does not lie symmetrically between H and Cl. It is not symmetrical. What does that mean? It means this shared pair of electron is shifted slightly towards chlorine. The reason being that chlorine is more electronegative. It is more electronegative. That means it has more tendency to attract electrons. Because of this tendency, the shared pair of electron will be towards Cl, like this. I should draw them prominently closer to chlorine, likewise, like so. So they are away from H towards Cl. This results in a partial negative charge over chlorine and a partial positive charge over hydrogen, and hence we call it as a polar molecule. It is like a dipole. And what is the direction of dipole moment? So it is a pair of equal and opposite charges separated by small distance. So in physics we call such a thing as an electric dipole. And what is its direction of dipole moment? Dipole moment is directed from negative charge to positive charge. So like so, this is the direction of dipole moment. So this is an example of polar molecule. So I have written P vector, direction is towards H, from Cl to H. There might be some confusion, students. In some chemistry textbooks you will find opposite direction of the vector. So don't confuse with that. The direction of dipole moment we will write from negative charge to the positive charge. On the other hand, non-polar molecule, for example H2, the one electron of this hydrogen and the other electron of that particular hydrogen, they share each other, resulting in formation of a covalent bond. Now because both of them are alike, H and H, their electronegativity values are same. Since their electronegativity values are same, these two electrons lie symmetrically between both these hydrogen. So neither of them develops a negative charge or a positive charge. So net dipole moment we say is 0 for H2. Hence it is a non-polar molecule. No poles are developed. So remember, there is a net dipole moment in case of polar molecule and the net dipole moment is 0 in case of non-polar molecule. Some other examples of non-polar molecules are like hydrogen, then we have O2, then we can have N2, we can have Cl2. All these are non-polar molecules. And examples of polar molecules, one is HCl, likewise we can have HBr, Hi, then we can have H2O and so on. There can be some other non-polar molecules like CO2, carbon dioxide. That is also a non-polar molecule. The reason being, here in the structure of carbon dioxide we have two oxygen sandwiching a carbon atom. Oxygen is more electronegative than carbon. I am not drawing the bonded pair of electrons. but they are identical both sides. So the shared pair of electron will shift more towards oxygen, resulting in development of partial negative charge over oxygen and partial positive charge over carbon. Now this pair is like a dipole. This is also like a dipole. For this, the dipole moment will be directed from negative to positive charge, like so. And for this CO bond, the dipole moment will again be from negative to positive charge. If you see these two dipole moments, they must be having equal magnitude, but their directions are opposite, and therefore they cancel each other, and therefore the net dipole moment is how much? It is 0. So this is all about polar and non-polar molecules. Remember, a polar molecule has net dipole moment, whereas in non-polar molecule, dipole moment is 0. This we say in another form, that in case of non-polar molecules, the centers of positive and negative charges coincide, and in case of polar molecules we say the centers of positive and negative charges are separated, and that's why the representation of a polar molecule will be like so. Will represent a polar molecule like this. That means it has a center of positive charge, it has a center of negative charge, and there is a separation between them. But a non-polar molecule, how will we represent? Will represent like this. There is a center of positive charge and there is a center of negative charge exactly on the same location. So this will be the representation for a non-polar molecule. So you have to remember this particular representation to understand the difference between polar and non-polar molecule. In polar, plus and minus should be separated a bit, but in non-polar molecules, plus and minus, they should not be separated. The centers of positive and negative charges coincide. So please note this carefully. This is the difference between polar and non-polar molecules. Okay, let us proceed further. Let us first discuss what happens in case of non-polar dielectrics. Suppose this slab represents a non-polar dielectric. So it constitutes of molecules which are non-polar. Now non-polar, what I have told students, they are such molecules wherein we don't have a net dipole moment, because the centers of positive and negative charge, they coincide like so. So I am representing only a few of the molecules. Likewise, you can draw many molecules over here. So the center of positive and negative charges, they are to be drawn together, because it is what kind of molecule? Non-polar molecule. Remember the representation which I had discussed just before this topic. This would be the situation if there is no external field. So E external is how much? 0. If this same dielectric slab is now placed in external electric field, these red arrows represent the direction of external electric field. That external electric field will exert force on the positive center and on the negative center, but in opposite direction. And due to these opposite forces, the two centers will get separated. Now imagine the force due to electric field on this particular molecule. So the positive charge will experience a force in the direction of electric field, and the negative charge will experience a force opposite to the direction of electric field, like so. So they will get separated. If they get separated, then you can understand from this, the plus should be shifted towards right and the minus will be shifted towards left, like this, resulting in a net dipole moment. Likewise, the same will be true for all other molecules. So the minus will be this side towards left, plus will be towards right. And like so. So this is in absence of electric field, this is in presence of electric field. So what do we obtain in presence of external electric field? We find that the individual non-polar molecules, their centers get stretched. here you should, is it not like stretching of this particular molecule? Why there is stretching? Because the plus and the minus centers are pulled in opposite directions under the influence of the external field. So remember this word, stretching of molecules results in net dipole moment. What would be the direction of dipole moment? You can see from negative to positive charge. So this is the direction of dipole moment. This is the direction of dipole moment. This is the direction of dipole moment. And this is same is true for all the molecules. So all these dipole moments are pointing along same direction, that is in the direction of external field. So the net dipole moment is developed in the direction of external electric field. In this figure, external electric field is towards right, therefore the net dipole moment will also be towards right. Now this is the reason, if you remember that figure which I had discussed earlier, that in external electric field, in case of dielectric also, here we have development of plus sigma p, which we have written plus sigma p, and this we have written as minus sigma p. You can see at this face you will have only plus signs, and at the other opposite face you will have only minus. If I draw this particular figure, some more number of molecules, you will find at the right end we will have only positive ends left, positive charges left, and on the left end we will have only negative charges left. So we say that the dielectric has got polarized, and this phenomenon is called as polarization. So this is true for case of non-polar dielectrics. In non-polar dielectrics, remember this word, stretching of the molecules results in dipole moment of the individual molecules which point along same direction in the direction of external electric field. This results in a net dipole moment. Next, let's see about polar dielectrics. So let's see about polar dielectrics. In case of non-polar dielectrics, we had seen that although the net dipole moment was zero in absence of external electric field, but when external electric field is applied, due to stretching, it results in a net dipole moment. The net dipole moment, which we write as p vector, was zero in case of non-polar dielectrics. Now you might think in case of polar dielectrics, the net dipole moment must not be zero, because they are polar molecules. Polar molecules we have represented like so, minus plus. Although the individual molecules have net dipole moment, but it is found that for the dielectric as a whole, the net dipole moment, sum of the dipole moments of all the molecules, is again zero only. Now how is this possible? Here temperature plays an important role. Now what is the role of temperature in these dipole moments? Yes, it has. Due to thermal agitation, or you can write due to thermal energy, the dipoles, the individual dipoles are randomly oriented. Now what is the meaning of randomly oriented? I have drawn one molecule. Do you think all the molecules I should represent like this only, such that their dipole moments should point in the same direction? Of course no. They are vibrating. Deep dielectrics have electrons. They are not free to move, but they can vibrate due to thermal agitation. More is the temperature, more will be the agitation, more will be the thermal vibration. So the orientation of these molecules may be along different directions like so. Now dipole moment is a vector quantity. This dipole moment is in this direction, this dipole moment is also in that direction, this dipole moment is somewhere here, here it is somewhere here, here it is in this direction, here it is in that direction. So due to thermal agitation, since the dipoles are randomly oriented, being a vector quantity, the individual dipole moments on adding vectorially will give resultant zero dipole moment. So individual dipole moments are not zero, but because of vector addition, they sum up to zero. Why? Because they are randomly oriented. This is the situation in case of a polar dielectric present in absence of external electric field. So there is a dielectric consisting of polar molecules, there is no external field. But if external field is applied, then like previous case, there may be some stretching, but the factor due to stretching is not that important in this particular case. Here another important factor plays a vital role, and that is reorientation. Reorientation of dipoles. Concentrate on this particular dipole. It has a dipole moment like this one. In presence of external field, you know, students, if you have external electric field and if you have a dipole, then what happens to the dipole? It experiences a torque, and due to that torque, it tends to align itself in the direction of electric field. So this dipole will try to align itself in the direction of electric field. Do you think it will align completely in the direction of electric field? It could, if it were free. If this dipole is free to move, it can do so. But do you think this dipole is completely free to orient itself? No. Why? Because it is present in the dielectric. There are other molecules exerting forces on the dipole. So it may be possible that complete reorientation may not take place. So these dipoles will reorient themselves, but may not reorient completely in the direction of electric field, but you will have orientation like so. I am just denoting the arrows. If you want, instead of arrows, actually you should have drawn symbols like this. So there are two factors, students. One is the external electric field, which tries to align the molecules or the dipoles in the direction of external electric field, and there is another factor, that is thermal agitation. So I am writing here, there are two factors. You should make a note. While making notes, please indicate these things, they are very important. What is one factor? One factor is temperature or thermal agitation. And what is the other factor? The other factor is electric field. What does electric field try to do? Electric field tries to align the dipoles. In which direction? In the direction of electric field or along E naught. What is E naught? E naught is the external field. Thermal agitation of the, or thermal energy, you can write thermal energy also. The thermal energy of these dipoles tend to disorient themselves. If you supply more amount of heat energy, there will be more vibration, there will be more randomization. So thermal energy tends to randomize. It tends to randomize. Randomize whom? Randomize the dipoles. These two effects are opposite in nature. So if you decrease the temperature and if you increase the electric field, more alignment will take place. If you increase the electric field, alignment will take place, of course, but then if you raise the temperature, there will be disorientation, there will be randomization. So both these factors play a vital role, and at equilibrium both of them balance each other. So here reorientation of the dipoles result in a net dipole moment. Here the net dipole moment was 0, but in this case the net dipole moment, which I write as P vector, capital P vector, or you can write P net, is not equal to 0. It has some non-zero values. Again you will find that on the right side, what kind of charges are there, students? It has positive charges, and on the left end, here it has, in this particular figure, it has negative charges. It again reminds of that particular figure which I have done earlier. So in presence of external electric field, here we have plus and minus charges developed like so, which creates an electric field which we have written as E in. So E in is opposite in direction to E naught, and therefore net electric field inside the dielectric is not equal to 0. Now this E in, how it develops, how we have positive and negative charges, surface charge densities, for that we had discussed first the case of non-polar dielectrics and now the case of polar dielectrics. If you remember just 2 words, students, I think you can write this entire explanation yourself. Figures you should remember. For non-polar dielectrics, it was stretching of the positive and negative centers which plays a vital role. And in case of polar dielectrics, it is the reorientation of dipoles which plays the vital role. So you should remember these 2 words, stretching and reorientation. Stretching in case of non-polar dielectrics and reorientation in case of polar dielectrics. These result in a net dipole moment. Let's see one term, linear isotropic dielectric. We have discussed whatsoever be the nature of dielectric, whether polar or non-polar. In both the cases there is net dipole moment. There is induced dipole moment. This induced dipole moment, if it is found to be directly proportional to the external electric field, and if it is in the direction of external electric field, then we say that such a dielectric is linear isotropic. Let me write its definition. So if the induced dipole moment, if the induced dipole moment in any dielectric be along external electric field and is proportional to the magnitude or the strength of electric field, then such a dielectric is called as what? Linear isotropic dielectric. It has a linear relationship with the electric field. Now there is a term called as polarization. So polarization we denote as capital P. These are some terms which you must remember. It is a vector quantity, of course, and it is defined as net dipole moment induced whenever a dielectric is placed in external electric field. We know dipole moment is induced. So the value of net dipole moment induced per unit volume is called as polarization. So polarization we can write as P net, that is net dipole moment divided by volume of the dielectric medium. So this polarization for linear isotropic dielectric, that means for those dielectrics for which this P net, or hence we can say P, is directly proportional to the electric field. So for linear isotropic dielectrics we can write the polarization is proportional to E vector. It is proportional to E vector means it is in same direction and it is proportional to the strength of this electric field. So this implies we can write P vector is equal to some constant into E. That constant we represent by the symbol chi. So how do we read this? This is read as CHI, chi, and chi E for electric. So this is referred to as electric susceptibility. So this is a constant. So P is equal to chi times E, where chi is known as electric susceptibility, or simply susceptibility you can write in this particular chapter, and it is a constant. Now can you think of the unit of capital P? It is dipole moment by volume. What is the unit for volume? Volume is meter cube. And what is the unit of dipole moment? It is a dipole moment, you know, charge into length. So it is coulomb times meter. So 1 meter will cancel, that becomes coulomb per meter square. So this is the unit for polarization. So this is a very important topic, students, polarization. Then we have susceptibility. This susceptibility chi can be related to your dielectric constant K, which I am not discussing in this particular lesson. We will proceed further to capacitors. There we will use some topics like in the presence of dielectrics, what happens to the electric field. Today we have discussed, let me tell you the result of that particular thing, you should remember that. So we had discussed that if there be a dielectric in presence of external electric field, let external electric field be E naught, then due to stretching or due to reorientation we develop E in, electric field within the dielectric, that opposes the external electric field E naught. So they are in opposite direction, but they don't cancel completely. So E net, which is E naught vector plus E in vector, is not equal to 0. That E net vector I will write as suppose E. Its value will be how much? E naught minus E in. Why minus? Because they are in opposite direction. E naught is the value of E naught vector, E in is the magnitude or value of E in vector. So E is equal to E naught minus E in. That means E, the net field inside the dielectric, is less than E naught. It is clear, E is E naught minus something. So this electric field is less than E naught. It is found that this net electric field inside this dielectric is given by the formula E naught by K, where what is K? K is dielectric constant, which is same as epsilon r, which you have read earlier. So remember, if you have a dielectric in presence of external electric field E naught, in absence of dielectric the field was E naught, in presence of dielectric the field will become E naught divided by K. Is this clear, students? Okay students, I will stop here. But before leaving, I would discuss one of the doubts. So I thought in this same video I should make this. Earlier I thought I should make a separate video, but I am continuing in this particular lesson only. This doubt is from your PT1. I don't remember the exact question number, probably it was number 3, but it may be some other number. The question was this, that there is some square and at each of the vertex of this square there is a charge Q, and you have to find the net force on any one of the charges. The side of the square is given to be suppose A. So suppose I choose one of the charges at one of the corners, say this corner. On this charge Q, these three charges will exert force. So this charge will exert a force in this direction. This charge will exert a force in this direction, and this charge will exert a force in that particular direction, that I will write afterwards. If this has value F, this must have value F. Why? Because the charges are same, the distance is same, and what is the value of this F? It will be 1 by 4 pi epsilon naught times product of charges divided by square of distance between them. So this is the Coulomb's law. Now if we have F and F, their resultant will be midway between them at an angle of 45 degree, and its value you can see, it is a square, it will be root 2 times F. So root 2 F is the resultant of these two forces, but there is one more force due to this one, and that charge will exert a force also in same direction. Suppose its force is F dash. So net force on the charge Q at this vertex will be root 2 F plus F dash. Now what will be our F dash? F dash is the force on this charge due to this charge. So 1 by 4 pi epsilon naught product of charges Q into Q by square of distance between them. Now this square, you can see Pythagoras theorem. This square is this square plus this square. So a square plus a square, that is twice of a square. So if you put these values, how much will you get? Root 2 times F. F is our 1 by 4 pi epsilon naught times Q square upon a square. And what is F dash? F dash is 1 by 4 pi epsilon naught Q square by 2a square. Things you can take it to common, and you will get one of the option as the correct. So this is the method for doing that particular question. In the next class, we would start a new topic related to capacitors and capacitance, and that will be last topic of this particular chapter. So read well, come prepared in the next class. Good luck students, see you in the next class. Thank you.